I'm honored to be here with you all today. I'm going to be speaking to you about integrated hydrogen production and consumption for improved utility operations. This is a project that we currently have ongoing with OUC, which is our utility here in Orlando. But I'm going to start off with a path to net zero emissions. And before I even get down that path, I want to explain to everybody that we have a lot of energy activity going on here at UCF. You may be familiar with a lot of the activities in mechanical engineering around combustion engineering. You may be familiar with the two clusters that we have. One of those clusters is more in the smart microgrid energy systems interaction, and the other one tends to be on the biomass CO2 catalysis. And then we have a lot of activities that are ongoing here at FSEC. But my point behind this is that UCF, basically in these colored leaves, is carrying out strong activities in all of them. And it's hopeful in the future that we all work together as a group to actually implement some of these activities and actually run our campus in a fossil-free way and lead to net zero efficiency, and then get energy efficiency improvements in our buildings. And then we'll be electrifying our transportation and so forth. So there's another thing that's unique about UCF, and that we actually have three rather large electric utilities that provide our electricity. Duke Energy provides electricity to the main campus, OUC to our downtown campus, and out where I am here in Cocoa, FPL is our provider. So we're somewhat unique compared to a lot of other universities in the United States. What I'm showing in front of you here is the actual global electricity generation mix. And you can see back in 1970, quite a bit of fossil fuels, a little bit of hydro. Presently today, the 2019-2020 timeframe, you can see the mix that we have there. I do want to point out that that's 24,000 terawatt hours that occurred in 2019. And by the time we get to 2015, in a business as usual sort of mode, you'll see that we'll have 69% renewables. 56% of that will be solar and wind. Okay, and that would lead us up to 40,000 terawatt hours in 2050. If we do accomplish that increase in renewables, by the time we get to the year 2050, we still will have a substantial amount of greenhouse gas emissions into our atmosphere. And typically you would see the scale that we've got across the top here. This is divided into power, which is the darker black, industry production, transportation, and buildings. To get below, this is about a 3-degree temperature rise. To get down to net zero emissions, we've got to get down to 1.5 degrees Celsius. And you can see then that we've basically got to cut the emissions from all of these four sectors. A rather busy chart. The chart over here to the left is looking at what we might do if we increase the electrification above and beyond business as usual. And you can see here that this would be the mix in here. There would still be some fossil fuels trying to fill in those areas that are very hard to transform with electricity, such as airplane flights and shipping and so on and so forth. The slide over on the right is looking at what would happen if we took this business. Here we are today at 24,220. If we go with the business as usual, we get up to 40,000 terawatt hours. If we go up with complete electrification, we get up to 65 terawatt hours. And if our goal is to do less than 2 degrees, we're going to go up to 102,000 terawatt hours, of which 75% of that would be wind and solar. And then a lot of that wind and solar will be used to go ahead and generate hydrogen. And then we can eventually get to the point where we're net zero emissions. To give you a framework where we've come with solar and wind, you can see back in the year 2000, there was effectively no wind and solar. You get out to the year 2020, today, we have over 2,800 terawatt hours of solar, but on this scale, relatively small. So this was an increase of 92 times from 2000 to 2020. To get to the point where we are at net zero emissions by 2050, we have to increase this 36 times. If you want to look at the percent of electricity itself that solar and wind provide, You can see we went from 0.2% to about 11%, but we've got to get all the way up to 84.5%. Now, fortunately, prices are going down, manufacturing is being increased, the applications, government subsidies. This is a good news story, okay? But to get all the way there, we've got to increase and do that in all kinds of ways. Now, hydrogen hasn't even gotten started on that same time scale. So if you look down at 2000, there isn't any. Relatively speaking, there isn't any in 20. To meet this 2050 target of net zero emissions, where we're needing to use hydrogen now as an energy storage, as a fuel, as an alternate chemical replacement. And Brian Pivowar will speak to you a little bit more details about some of this than I am later on. You see, we've got to really move up the petajoules of hydrogen. You'll also know that the amount of green energy going to make hydrogen, which is 0% today, we'll be using about 58% of the wind and solar will be used in 2050 to make hydrogen to meet these targets. So you can see, hopefully, the trajectory we've done with solar, what we've done with LEDs, what we've done with lithium, what we're doing still with lithium-ion batteries. We'll be able to do these same kind of things in the hydrogen arena as we go forward. And it requires everybody who's engaged in the scientific community to be involved with that. Now I'd like to speak to you a little bit about our project. So this project is actually demonstrated in integrated hydrogen production and consumption for improved utility operations. So in the case of OUC, they have solar fields. Their solar electricity would come into an electrolyzer. That electrolyzer, which splits water to make hydrogen and oxygen, is a utility controlled asset. Traditionally, the utilities don't control their loads. They do control batteries, but in this case, they would control an asset. You could then use that hydrogen to run it back into a fuel cell, a stationary one, and put electricity back on the grid, much like a battery would. Though in this case, you separate a battery because you have a tank of which you can store a lot of energy with it. You can also mix this and put this back in a natural gas pipeline and put that into the existing turbine infrastructure. You would then also have the ability to use the hydrogen if you'd like to run fuel cell vehicles. So in our demonstration, this would be bucket trucks and so on and so forth. So you have this opportunity to optimize this whole system to minimize the cost as you add more solar onto the grid and you need more and more storage. How do you optimize that system to enable it to work and be cost effective? That's our goal. This is a standard hydrogen at scale slide that I've swiped from Brian multiple times before. He'll go into more details with you. But as you look at this whole infrastructure of where hydrogen fits, the actual project that we're dealing with is renewables. It's got the electric grid, it's got power generation, and it's got hydrogen generation. And we're going to then feed the hydrogen to a vehicle. But you could feed this hydrogen into metal refining and other activities, fertilizer manufacturing, and so on and so forth, using that hydrogen to make synthetic fuels from biomass. This gives you a flavor of what the activity is. Our overall goal here is to ensure that the hydrogen is produced at the lowest electricity cost and then consumed for the greatest possible value. And then the goal is to come up with new business models. Okay, our utilities traditionally have provided you with electricity all the time. I think in the future, utilities will be more interested in you with providing information about the optimal flow of those electrons around, more than their emphasis in actually generating them. And then you have all kinds of other technologies that would be coming onto the grid, as well as the fact that transportation will move forward with this. So a lot of this activity has also come up with new business models. This right here is a curve that the National Renewable Energy Lab came out, where it studied the state of Florida. And this is what they call their high ramp curve. So as you add more and more solar, which is depicted by these yellow lines on here, you can see that if we get up to 45% solar, we actually would be turning off all the fossil fuel plants in the middle of the day, because the sunshine in Florida would be creating so much electricity that we wouldn't need to run those power plants. Now, that's not good for the power plants. And you can see here that there would be a 50 gigawatt in 2-hour drop as we add more and more turbines on. If we take more solar on and take our turbines off, that leads to a drop in that generation of the turbine. And then sure enough, when the sun stops shining, we have a huge increase that's coming in. So using long duration storage from something like hydrogen could enable us to continue to run those turbines and mitigate, oops, I switched the slide somehow, back. I'd like to also point out over here to the right, the sun doesn't shine all the time during the day. And quite often in the Orlando area where we're all from, we get cloud covers. And so you can see the left plot is more of a long-term duration issue concern and ramping for utilities. The one on the plot on the right is cloud cover issues. So you can see where in this case, this was a 8.9 megawatt solar field in Orlando. It's a fixed axis. It's fixed axis. It's located at the Stanton power plant. That you could get drops of 6 megawatts. More than 2/3 of the energy just disappears real quick. And so obviously that leads to fluctuations in the grid. I will also point out that today, OUC's installed solar is about 3% now. It'll be about 10% by 2022 and up to 20% by 2024. So you can see the graph over on the left shows that OUC as a utility is going to have to be dealing with these ramping up and of their combined cycle natural gas plants as they add solar on. And hydrogen can be used to solve some of these problems. This is actually a schematic of the project that we're dealing with. OUC actually has a nano grid over at one of their facilities. They have some small flow batteries with it. They have floating PV. They actually have a building load associated with it. Right now in our interactions with Plug Power and OUC, the intention is to put a 500 kilowatt electrolyzer there, a 600 kilowatt stationary fuel cell, and then to use 2 bucket truck types of things with dispensing and the manifolding of that. At the same time, being able to use mobile hydrogen as a mobile storage trailer and use a 300 kilowatt deployable fuel cell. So a mobile fuel cell, if you will, for backup power somewhere else. And so this is the project as a demonstration that we're carrying out. And we're in the first year of the 3-year demonstration project. As part of the activities, as I mentioned, we at UCF are to study and do the systems optimization of this project. In the case of cloud cover, we need to be able to dynamically operate these electrolyzers and perhaps the fuel cells as well to go ahead and put power onto the grid in a timely fashion. So you can see that it's a very complicated system and we're interested in optimizing that. I need to move a little bit quicker here. These are some examples of some solar data from that same field I mentioned to you. You don't see the beautiful Gaussian distributions. These are 5 of the worst days in a whole year. And you can see how the PV really fluctuates around substantially. And what we're trying to do is have the electrolyzer run at a steady value and then turn it off whenever need be to try to smooth out these curves. Okay. And here's some examples of the smoothing that we actually did and their hydrogen outputs. And so we're doing a lot of study with that project. To move along, I want to talk to you a little bit about another project we're doing. We're actually using an IEEE 33 node distribution system network where we actually have small gas turbines, small combined cycle natural gas plants. We have PV, we have battery energy storage, and we have 33 critical loads. And what we're trying to do is to optimize this system, looking in as the costs go down as to how you could operate the system at 100% renewable going into the future. And so I'll do this sort of quickly here. This is the example of that system, generation versus load, with only using fossil fuels. And so you can see this is over a 2-week period of time, and you can see the 3 fossil fuel power plants operating. They do have ramp restrictions and so on and so forth, and we have to maintain grid integrity and voltage losses on the distribution. If we add a substantial amount of solar, you can see that the orange colors drop off, and the solar is the green is providing that during the day. But at this substantial amount of solar, you can see that we're curtailing a lot of it. And the green energy production here is 50%. And we have a lot of issues associated with ramping rates with the fossil fuel power plants. If I go ahead and add a 10-hour flow battery and then add hydrogen storage, you can see that we can almost get to 100% renewables. You can see that we're still using a substantial amount of solar. And not curtailing all of it like I did earlier, but at the same time, we're able to go ahead and use these devices to get us to the point where we can operate almost at 100% renewable energy. This is my second to my last slide. Brian will talk to you about the fact that the Department of Energy is standing up a lot of hydrogen hubs. They would be regional hydrogen hubs to do large-scale demonstrations. We have already stood up a Southeast Hydrogen Energy Alliance. You'll notice the states that are listed here. Florida is a very important one of those. And we had our conference yesterday, of which 214 people that are interested in working together with this are ongoing on. If you're interested in this, please send me an email, because there are several working groups that are involved in all the activities associated with this for us to get an application in to locate a hub. And this would require demonstrations in all states within our regional hub. And then I'll end with, it's now cheaper to save the climate than it is to destroy it. Thank you.